All right, so 4.1 we dealt with what kinds of triangles? Right triangles. And we have wonderful features about right triangles that are all useful to us. We've got relationships of between the side lengths. What's the relationship between the side lengths on a right triangle? Pythagorean theorem, a squared plus b squared equals c squared, exactly. So we have that relationship. We also have relationships between the sides and the angles, and that's the SOHCAHTOA information, right? Sine, cosine, and tangent, and we have this different relationships we can set up. And that's great when we have right triangles, but none of that works the same way if the triangles are not right triangles. So what we're going to be looking at in sections 4.2 and 4.3 is and maybe 4.4, I can't remember, but at least 4.2 and 4.3, we're going to be looking at a couple of different laws. We're going to be looking today at law of sines, and we'll finish that up on Wednesday, and then law of cosines is next. Law of sines and law of cosines work just fine with right triangles. You can use them for right triangles, but it's kind of like overkill, right? I don't need to grab, a textbook to squash the fly on the wall. A fly swatter would work just fine. Okay, so it's just more than I really need. I've got other relationships that are easier and quicker to use for right triangles. However, these relationships that we're about to establish work really well when I can't use those. Namely, I don't have right triangles. Okay? So if you get in a frenzied hurry and you use one of these law of sines on a right triangle, it's not going to give you a wrong answer. You don't have to worry about that, okay? But it is just using more information than you needed. All right, so we're going to start with law of sines. Law of sines has what looks like a triple inequality, okay? So we have A over sine A. Notice the capitals versus the lowercase because that's important. B over sine B equals C over sine C. And I went ahead and put the disclaimer on the bottom, although we've already talked about it before, that angle A is across from side A, angle B from side B, and angle C from side C. Okay, so the capital letters are angles, and the lowercase letters are the opposite side of that angle. So let me draw a picture for this. So we've got some kind of a triangle, and I'm drawing mine at the moment anyway as obtuse. We could draw it as acute, and that would be okay as well. They could have sides that match, so it looks kind of like the second picture that I drew has maybe an isosceles triangle. That can happen. It certainly wouldn't have to. No matter where you draw or how you draw this, angle A is opposite side A, angle B is opposite side B, and angle C is opposite side C. And there's no indication like we did before when we were working with right triangles is that we virtually always let the angle C be the 90-degree angle, right, the biggest angle. We don't have any of that here. So the angles can be in any order, anything. There's not a common practice for that. Okay, so you can put them wherever you'd like. The one thing I want to talk to you about the law of sines is that it looks like you have three separate fractions that are all equal to each other, and that's true. But what you do when you use the law of sines is you use whatever two pieces of information you need at a given time. So if I want to find something out about sides A and B, I'm going to use this portion of the triangle, or of the equation. If I want to find something out about sides B and C, I would use these two pieces. All right? You never use all three at once. Or if I want to find a relationship between A and C, I use the outer two pieces and set them equal to each other. So you're just using two pieces at a time. It's just that all three of the pieces are in fact the same. So everybody tracking with me on that? We're all good? Okay. So let's take a look at solving a triangle. So just like before, when we solve triangles, we have to find all the missing pieces of the triangle. But we have no 90-degree angle to work with, so sometimes that makes it a little bit more challenging. So we have angle A given to us. On your paper it has this. I didn't get that in on my slide yet. 87.2 degrees. We have side B given to us, which is 75.9 yards. And I have angle C given, which is 74.3 degrees. Now, when you take a look at this, I can draw a picture, and my picture, whenever I draw a picture, they're never going to be drawn to scale. I tend to always draw my triangles the same way, and they all kind of look like they're acute, and sometimes they look even like they may be isosceles or equilateral, okay? So there's nothing drawn that way to indicate that that's really happening. I tend to put A on the bottom, and B on the top, and C on the side, but it doesn't really matter. I just need to place them in there. So angle A is 87.2 degrees. Angle C is 74.3 degrees. And side B, which would be opposite angle B, so down here on bottom, is 75.9 yards. Now, there's two reasons that we're about to do what we're about to do. There's three pieces of information we don't know, right? We don't know angle B, we don't know side A, and we don't know side C, correct? One of them is easy to find, which is the angle. Not only is it the easy one to find, we have to find it first. The reason we have to find it first is because take a look back at this inequality. In order to use any two pieces, and I don't care which two they are, of this inequality, you have to know a side and its opposite angle, or an angle and its opposite side. And in this picture right now, I don't have that information. Do you see what I mean? So even if it weren't the easiest thing to find at this point, I'd have to find it first to be able to continue with the problem. So, and in this one, of course, unlike with my right triangles, I don't have the ability to just take something away from 90. I actually have to take and find the information itself. So, angle B. How am I going to find angle B? Okay, so these are all degrees, so we'll list them all as such. So you can either subtract each one of them from 180 like this, or if you really want to, I know some of you think about this differently and you say, oh, I'm going to add the 87.2 and the 74.3 together and then subtract it from 180. Of course, you're going to get the same thing either way. What do we get for angle B? Okay, did everybody get 18.5? Perfect. All right, so now that I have 18.5, I have a side and its opposite angle, or an angle and its opposite side, okay? So I'm going to be able to use angle B and side B as a pair in my inequality. So side B is 75.9. Angle B means I'm going to have sine of 18.5 in a denominator. Now, somebody pick for me, do you want to find side C or side B first? I'm sorry, side C or side A first? A. Okay, so we'll find A. So I'm going to find A, and A is related to its angle A, which is the sine of 87.2 degrees. So far, so good? So you see just two pieces of the inequality, or of the equality set up. You can cross multiply if you'd like. Again, cross multiplying happens to be overkill here because I really want A alone, which means what I really want is I want this piece to move to the other side. That's the only piece that needs to move. So I'm not going to cross multiply. Again, you can. It's not going to hurt anything. But I'm going to take this sine 87.2 and multiply that to the 75.9. So I have 75.9 sine of 87.2 degrees over the sine of 18.5 degrees. Is everybody okay with how I did that? All right. What is side A? I hear lots of calculators going. That's good. Did you get a value, Michael or TJ?
238.92.
Thank you. We got some units on there. Shake your head if you got the same value. Did it work out in yours too? Okay, good. I've got confirmation across the board. So there's side A. And I need to find one more side, right? So I do the same thing again. Do I have a blank slide here? Of course not. All right, so I'm going to have that same 75.9 over sine of 18.5 degrees. And I'm going to find side B now. And that's not B, sorry, C. Side C. And side C has an opposite angle of 74.3 degrees. So this will be sine of 74.3 degrees. Do not be tempted to try Pythagorean theorem. That's not going to work here. Why not? Yeah, because I don't have any 90-degree angles, right? So if you were tempted to try to do that on the last section, it would have worked out okay. You may have lost some accuracy. We talked about that last time. But it's absolutely not possible here because these are not right triangles. All right, so I'm going to multiply the other side. So I have C equals 75.9 sine of 74.3 degrees. Again, if you want to do cross multiplication, that'd be fine. You'll just have one extra step. Divided by sine of 18.5 degrees. What do we get for side C?
130.29.
Is that good? All right. Again, let me reiterate one thing in this one is that you want to make sure that you're not using information you were not given. Right? So we want to avoid using for instance, I wouldn't want to change this and use side A to find side C because I introduced some rounding error when I did that, or TJ did, or whoever told me the numbers, right? Because that's what happens when we have to solve these, right? We eventually have to say a certain number of decimal places, and we do have rounding going on. So please make sure you're using the information you were really given. And the 18.5 for the degrees here, we have to use. We don't have a choice. But there was no rounding error when we found 18.5 either, was there? No, because it was just subtraction from 180. So I didn't have any errors possible from that unless I just made an error and calculated it. But there's no rounding error possible. So, any questions on this one? Okay, let's take a look at an application problem, I guess you'd say, of law of sines. All right, so does anyone go skiing in the winter, snow skiing? Oh, I have a couple people that said they do. That's it? Nobody else snow skis? Robert does? Okay, so if you've never been before, you've never seen the ski lifts or whatever, so you're going to have to imagine a little bit. But when you're going on a ski lift, you have to ride up a lift to get to the top of the hill, okay? At least unless you're doing something really cool like, if you're doing something really cool like them taking you up where you're like not supposed to ski and like a snowmobile, that may not be true. But most ski slopes, this is the way it would work, right? So you've got a, let me draw it this way. You've got a lift that is in no way, shape, or form this steep. But I'm going to run out of space if I'm not careful, okay? And you start at the bottom, and you get on a little chair, and the little chair, here's your person, and the little chair takes you up to the top of the mountain where you get off, okay? And it's at some sort of an angle here. And it says, okay, so, and they're giving us some letters, so we're going to put the letters in as we go to make sense of this. It says to find the length of the span of a proposed ski lift. So this is the length of the lift from P to Q. So we're going to put him down here at the bottom at P, and you'll see why in a minute, and Q at the top. A surveyor measures angle DPQ to be 25 degrees. So the angle has to measure at angle P, and this right here is my D. Here's my 25 degrees. Most of the ones you deal with that use letters actually have pictures in your book, okay? And this one actually did too. So we have a 25-degree angle. He walks a distance of 1,000 feet to R. Again, you're going to have to take my word for it that the picture is supposed to look like this a little bit. Here's my 1,000 feet. He stops right here. And here's R. And we got 1,000 feet here. And then he measures this angle PQR. Right here, this angle, whoops, to be 15 degrees. Okay? And the question is, what's the distance from P to Q? So P to Q is over here, and we'll call it maybe X. Okay, so do you see a triangle? We've got this triangle. I have the side length x that I'm looking for. This is definitely not a right triangle, right? I'm not going up the mountain vertically. That's not happening. So this can't be a right triangle. And you come over here, you've got a 15-degree angle down here. Now this 25-degree angle is actually not part of my triangle, but it gives me some information about my triangle. What information will it give me? This angle inside of here. This is a geometry concept, right? Again, kind of like we just did a minute ago with the angle of elevation. This angle right here, what will it be? 155. Why? Right, and we did this way, way, way back at the beginning of the semester, right? This is actually a straight angle, so it has to add up to 180, and here's 25, and then that piece would be 155. So my picture actually has an angle of 155, an angle of 15, and an angle at the top, so this angle right here is 155. And I have an angle at the top that I, quote unquote, don't know. But I could certainly find it. In fact, I need to find it. Why do I need to find that angle? Because it didn't ask me to find that angle. Because I need to use sine. Okay. But why can't I just use the two angles I was given? This side on the bottom, right? The side information that I know is the 1,000 at the bottom of my triangle. So in order to use that 1,000 little yellow piece at the bottom of the triangle, I have to know its opposite angle. The opposite angle is the one at the top that I haven't written in yet. So how am I going to find this angle at the top? So 180 minus 155 minus 15. And what is the angle? Okay, me and this computer is not working today. Okay, I can't get my degree marker on there. Pretend they all have degrees on them, please, okay? Because this is just not working. I don't know what's wrong with it. All right. What am I looking for? I'm looking for x, though, right? And I can use the law of sines for this because I do have a pair of opposite angle, opposite side that I know. Well, let me try this. Helps for now. Okay, and I need to set up my law of sines. So what will that look like? Does everybody understand where all those pieces came from? Yeah? Okay, so we can do the same kind of thing I did back on the previous slide. I really just need to get this piece right here to move, right? So I can really just multiply it to the other side. So I have x equals, I have my 1,000 sine of 15 degrees over the sine of 10 degrees. What'd you get? 1,490.48. Sound good? Any questions? We're about to hit something very interesting. All right. There is something weird that can and sometimes does happen when we use law of sines. And that's actually called the ambiguous case. So when we're using the law of sines, one of three things can happen. Now, I didn't sort of mention it before because it didn't happen on the last two problems, okay? But if you take a look at your sheet of paper, right, you notice that it has a possibility of different numbers of triangles occurring. Okay? First question is, when could it happen? And it happens or has the possibility of happening when we have side-side angle. Is there something that you remember about side-side angle from geometry? What do you remember? Yep, that's area. Do you remember back in geometry when you did proofs of triangles being congruent, and you had different, I don't know if they would have called them theorems or lemmas or something. They gave them names in your textbooks. And there were things that were called the side-side-side theorem, and the angle-angle-side theorem, and the side-angle-side theorem. And somewhere along the way, I am just certain that if you encountered this material, some teacher told you, there is no formula for side-side angle. And the way you can remember it is because if you turn the word around, it's not a word you're supposed to be saying in class, right? Okay. So one of those, reminders to yourself. And the reason that there was no formula or no proof or theorem that was able to be used back in geometry is because of what you see happening here. Okay? So one possibility when you have a side, and an excluded angle, okay, given, then you could have no triangles formed. So this is the picture you're seeing down here. So here's my side, and here's another side, and this is an exterior angle. So in other words, the angle's not between them, okay? So we always describe these different theorems in geometry based on where the location of the different pieces are. So if this angle had been right here, we would have called it side, angle, side. Okay? So you can either call this one side, side, angle, or you can call it angle, side, side. But that's what you're looking at here, is that's the arrangement. So you could actually end up with the pieces of information not giving you a piece right here that's long enough to form a triangle. I don't care how I draw this. So it sounds like kind of like, how will I know when in the world would I have no triangles? Well, believe it or not, the no triangle case is the obvious one. You'll know that it'll happen because you'll at some point get an angle where it says something like this. You'll have sine of angle A equals 2.3. Sine of angle A equals 1.07. Sine of angle A equals 3.72. What's wrong with all of those? It's not within the restriction. What's the restriction for sine values? Negative 1 to 1. So it's really obvious. And if you don't even remember it and you try to tell your calculator to do it, it'll give you an error. And it'll say something like error domain or invalid domain or something like that. It'll tell you that that's not going to work. Okay? So the case when you have zero triangles is the easy case. And it's very obvious when it happens. Okay? Now, the case that we just encountered on the last two examples was the second one of these one triangles. I actually encountered this piece down here. And I think I have more picture drawn than I actually intend to have here drawn. I'm not sure if I can fix it now. This is what happens when you're trying to draw all three of the pictures and you get them confused. Okay, so it looks something like that, I think. Except that the sides look fuzzy now. But anyway, so we have a possibility then of our triangle forming a right triangle. Certainly a possibility, no problem. Or we have a triangle formed that is not a right triangle, but still there's just one of them. Right? And this would be sort of what we would think we are always going to have. In fact, you didn't know it, but right, we did two examples where we only had one triangle formed. Now, let me show you that we actually didn't have side-side angle in the first problem, did we? Notice the pieces of information we were given. We were given an angle and a side and an angle. We were actually given angle, side, angle in this problem. So that has no possibility of this running into the ambiguous case. The only time the ambiguous case is possible is when we have side angle given. Okay? So you don't have to worry about it on that one. We had the same thing here. We had two angles and an included side. We actually had angle, side, angle on this one as well, just like the last one. And on this case right here, we do have a possibility, even if we have side angle, of having just one triangle. Okay? The third possibility, and the one that creates the most work for us, is if there's two triangles in the problem. So imagine that you were given, again, side A, side B, and angle A. Okay? Well, the location for side A could come out here to where B2 hits the horizontal down there. Or side A could swing back the other direction and hit where B1 hits the triangle on the bottom. There's actually two different triangles that could be formed based on the dimensions that were given. Okay? And this is the reason that back in geometry you had no side angle theorem, is because both of these angles, these have the same sides, the same two sides, and the same excluded angle, And these triangles are not congruent. And the actual triangles that I'm imagining here, and I want to draw them just to make sure everybody's with me, is that I have one triangle here in purple, right? And then I have a second triangle here in red. And those are not congruent triangles. They are not equal triangles. They do not have all their sides and angles equal to one another, right? But they do have the two sides A and B and the angle A that are congruent to each other. Okay? So we're going to stop there today, and we will pick up with showing and seeing how we actually figure out which case we're in on the last 3 examples next time.